We've seen that a line integral of a function f of x, y, z with respect to a curve c is computed by creating a parameterization for c called r of t, plugging it into f, then multiplying by the magnitude of r prime of t to substitute dt for ds. Now we're going to compute a surface integral. This is a double integral of a function f of x, y, z over a surface S. Notice that because surfaces are two-dimensional, this creates a double integral. Again, how do we compute this? The process is similar to line integrals. We first construct a parameterization for S as r of uv, where u and v are parameters defined in some domain space D. F of r of uv restricts our function f to the surface S. Now we want to convert ds to be defined in terms of du and dv, or in other words, dA. Recall that when we did surface area, the ds differential was converted to dA by multiplying by the magnitude of the cross product of the tangent vectors of r with respect to u and v. So this converts our integral to our variables u and v. Putting this together, we compute the surface integral by computing the double integral of f of r of uv times the magnitude of the cross product of r of u and r of v over the domain D. Let's do an example. Suppose we want to compute the surface integral of x plus y plus z over S, where S is the parallelogram with parametric equations given here, where u ranges from 0 to 2 and v ranges from 0 to 1. First, let's set up r of uv and compute our tangent vectors. R of uv equals u plus v, u minus v, and 1 plus 2u plus v, so r of u will equal 1, 1, 2, and r of v will equal 1 minus 1, 1. When I take the cross product of these two vectors, I get 3, 1, minus 2. The magnitude of this vector is the square root of 3 squared plus 1 squared plus 2 squared, which equals the square root of 14. When I substitute r of uv into f, I get uv plus u minus v plus 1 plus 2u plus v, which equals 4u plus v plus 1. Putting this all together, to do the surface integral for f on S, I compute the double integral of 4u plus v plus 1 all times the square root of 14 for u from 0 to 2 and v from 0 to 1. This comes out to 11 times the square root of 14. If S is given as the graph of a function z equals g of xy, instead of parameterization, we can use an alternate formula. The surface integral of f over S is computed by substituting g of xy for z, and multiplying by the square root of the partial of g with respect to x squared plus partial of g with respect to y squared plus 1 times dA. The domain D depends on x and y. Let's do an example. Let's compute the surface integral of z squared over S, where S is the part of the plane 2x plus y plus z equals 4 lying in the first octant. To start, let's first draw a picture of S to help us identify the bounds. The domain we're going to integrate over is the triangle D in the xy plane. This side is where z equals 0 in the plane equation, so 2x plus y equals 4. The domain D can be described as y between 0 and 4 minus 2x, and x between 0 and 2. The surface S can be described as z equals 4 minus 2x minus y, so this is our function g of xy. We can then compute the partials of g. The partial with respect to x is negative 2, and the partial with respect to y is negative 1. Z squared in the integrand becomes 4 minus 2x minus y quantity squared. So we can put this all together in the formula for surface integrals to get the double integral of the square root of 6 times 4 minus 2x minus y squared, as y goes from 0 to 4 minus 2x and x goes from 0 to 2. Working this out, it comes out to 32 over 3 times the square root of 6. Now, just like with line integrals, we're going to do surface integrals of vector fields. We had to be careful about the direction on line integrals, and we're going to have to be careful about direction here too. How we talk about direction with surfaces is with orientation. An orientable surface has two well-defined sides. In other words, at any point, there are two unit normal vectors as shown in this drawing. If the surface is closed, meaning it's the boundary of a solid E, then there's an inside normal vector and an outside normal vector. We call positive orientation the side where the normal vector points outwards from E. For example, if S is a sphere, the inside normal vectors have negative orientation and the outside vectors have positive orientation. If our surface S is given by a parameterization r of uv, the positive orientation can be computed from the parameterization. It's the cross product of the tangent vectors divided by the magnitude of the cross product. Notice that this vector will be perpendicular to the tangent plane, making it normal to the surface, and dividing it by its magnitude makes it a unit vector. We're now ready to set up surface integrals of vector fields. Suppose we have a three-dimensional vector field defined over an oriented surface S with unit normal vector n computed as before. The surface integral of f across S is given using this notation and can be computed by taking f dotted with the normal vector n over S. However, remember that n equals the cross product of the tangent vectors divided by the magnitude of the cross product, and ds equals the magnitude of the cross product times dA, so we can simplify this to be the double integral of the dot product of f of r of uv with the cross product of r of u and r of v. The surface integral of a vector field is called flux. This is the flux of f across S. This has physical meaning. If f is the velocity field of a 3D fluid flow, the flux of f across S is the net rate at which the fluid is crossing S. Again, if S is given as the graph of a function z equals g of xy, then we can use an alternate formula for flux. If f is given as p, q, and r, then the surface integral of f across S is the double integral of negative p times the partial derivative of g with respect to x minus q times the partial derivative of g with respect to y plus r. Let's do an example. Let's find the surface integral of f across S, where f is the vector function 0, y times z, z squared, and S is the surface cut from y squared plus z squared equals 1, z greater than or equal to 0, by the planes x equals 0 and x equals 1 with upward orientation. In other words, find the flux. First, let's draw S. S looks like a tunnel running along the x-axis. The region we'll integrate over for x and y is the rectangle running from x equals 0 to x equals 1 and y equals negative 1 to y equals 1. Because it's only the top half of the cylinder, we can solve for z. Z equals the square root of 1 minus y squared. This is our function g of xy. The partial derivative of g with respect to x is 0, and the partial derivative of g with respect to y is 1/2 times 1 minus y squared raised to the negative 1/2 times negative 2y, which equals negative y over the square root of 1 minus y squared. Now let's identify our p, q, and r. P equals 0, q equals y times z, which equals y times the square root of 1 minus y squared, and r equals z squared, which equals 1 minus y squared. We can put this all together. Our double integral will have integrand 0 minus y times square root of 1 minus y squared times negative y over the square root of 1 minus y squared plus 1 minus y squared, which simplifies to just 1. So we're integrating 1 over the rectangle, which comes out to 2. Remember that for line integrals of closed curves, we had a way to convert from the line integral of the vector field f along the curve to a double integral of the region inside the curve. This was Green's theorem. For surface integrals, we have a similar result. Now we have a closed curve that's the boundary of a 3D surface. We have to keep track of the direction on C and the orientation of S. If we walk along C with positive orientation, with our head pointing in the direction of the positive normal vector, the surface will stay on our left. See the picture here. With this, we can state the 3D analog for Green's theorem called Stokes' theorem. Suppose we have an oriented piecewise smooth surface S that is bounded by a simple closed piecewise smooth curve C that has positive orientation. Let F be a vector field whose components have continuous partial derivatives on a region that contains S. Then the line integral of F along C is equal to the surface integral of the curl of F along S. Let's do an example. Suppose we want to evaluate the line integral of the vector f along C, where f equals x times z, x times y, 3xz, and C is the boundary of the portion of the plane 2x plus y plus z equals 2 in the first octant, traversed counterclockwise as viewed from above. Let's first draw C. C is the triangle with vertices on the axes, x equals 1, y equals 2, and z equals 2. Notice that if we wanted to compute this as a line integral, we'd have to do 3 separate line integrals and add them up. Now let's observe that C encloses a surface S, which is the filled-in triangle. If we want to use Stokes' theorem, we'll have to do a surface integral over this triangle of the curl of f. Let's first figure out how we'd compute this surface integral. S can be described as the graph of the function z equals 2 minus 2x minus y, so we'll use the graph formula for the surface integral. The region we're integrating over is the triangle D in the xy plane, given as x running from 0 to 1 and y running from 0 to 2 minus 2x. To use Stokes' theorem, we'll need to use the curl of f. The curl is computed as the cross product of f with the nabla operator shown here. We can compute that the curl of f is 0, x minus 3z, and y. When restricted to s, z equals 2 minus 2x minus y, so I'll plug that in for z in the second component. When using the formula, our p will be 0, our q will be 7x minus 3y minus 6, and r will equal y. Now I'll plug everything into the surface integral formula. The partial of g with respect to y is -1, so this simplifies to the double integral of 7x plus 4y minus 6 over the region D, so we have y running from 0 to 2 minus 2x and x running from 0 to 1. Integrating this out, the answer comes out to -1.